Hello, it's Mr. Rops here, and today we're going to talk about hypothesis testing. And this is a really big deal in inferential statistics, and this is really what we do every time. And I've kind of hinted at it when we've done confidence interval, but here we're going to get into it for real. And so what we're going to do, and I did this in class a number of years ago, and so we are going to determine whether we are being cheated out of M&Ms by the M&M company. You will conduct a quality control experiment to assess whether the Mars Corporation, who makes M&Ms, has correctly labeled the weight on the M&M bags. And the weight on the M&M bags, if you look down here really carefully, magnifying glass, is 50 grams. Okay, and so the requirements, everyone needs a M&M bag and scales to weigh it. And so what are the hypotheses in this experiment? Well, the hypothesis, we have the null hypothesis, is h, 0, is that the assumption of what is the current true value is still true. We assume that the mean of Mars bags is 50 grams. That's our null hypothesis. We assume that that's true. And our alternative hypothesis, which is h sub a, or sometimes it's h sub 1, we are trying to assume that the null hypothesis, well, if we're being cheated, that means it's going to be less than 50 grams. Okay, and this is a one-sided test. This is a one-tail test because it's less than. If we wanted to see if there was more than 50 grams, well, I would look at more. That would be a one-tail test as well. Sometimes in hypothesis testing, though, we want to see the null is that it's equal, and the alternative is that it's not equal to 50 grams. But for our and that would be a two-tail test. But for our particular example, we want to see if we're being cheated, and so we're looking for less than 50 grams. All right, so in order to do that, we have to look at some assumptions. Well, we are going to assume that our 20 bags are independent of each other, So the probability that one bag is different than the other bag, or that they're all the same, they're not related, is true. And so I want to think, is this going to be true or not? Well, if I consider the bags that I probably got were 20 in the grocery store at one place, and once are all side by side, this is probably probably not met, so it's false. So this assumption is not met. The other assumption we have to make is that the weight of M&M bags comes from a normal population. The weights are normal. Or if they're not normal, then that n is bigger than or equal to 30. So therefore, we could use the central limit theorem. And again, in this particular scenario, we have no idea if it's normal or not. So again, this condition we do not know. Our sample is going to be 20. So for sure, this part's not met. But even though our assumptions are not met, we're still going to go ahead and go with the program. And so previously, I have come through and I've measured these 20 bags, and miraculously, you're going to see the next slide that will have the weights. And so here are the weights of the 20 bags. Here they are all written. And I've taken the liberty to find the numbers. I know there are 20 bags. The mean weight of all 20 of these bags is 49.52. And the standard deviation of the unbiased one, okay, the unbiased standard deviation is 2.74. And I'm going to use, because it's an estimate, I am going to use the t-distribution of degrees of freedom of 19. And I'm going to do in total a one sample, because I have just one data thing. I'm looking at one sample t-test of degrees of freedom 19. Here I've named the test, and I have my numbers. So the next thing I want to do is I want to test my hypothesis at an alpha level of 0.05. We're going to talk more about what that means in just a moment. That 0.5 significant levels is alpha. Be sure to include your test statistic and the degrees of freedom where applicable. Well, I've already named my test. I've shown the numbers. Now I have to show my computation. So what I'm going to do is I'm going to do one sample t-test. I'm going to go to stats. And I'm going to go to the tests here. And I'm going to do number 2, a test. I don't have the data. I do have the statistics. So I know the mu hypothesis is going to be 50. Not 750, but 50. And delete that. And I know that the mean of my sample, let's try this again. Okay, so the next step is I'm going to take these numbers and I'm going to test my hypothesis at an alpha equals 0.05 level of significance, which I'm going to explain more about that in a while. I have to include my test statistic, degrees of freedom, which I've already mentioned, and the p-value of your test. And all these are new pieces for you. So let's go and talk about them. So what I'm going to do, I'm going to take this data and I'm going to go to my calculator. I'm going to go stat, test. I'm going to do a number 2, which is a t-test, because I do not know the true population's standard deviation. So I'm going to use statistics because I've just have these numbers. I didn't actually put the data in. I know the null hypothesis is, if I look back to the initial one, is 50 grams. So that's the mu of the null hypothesis. And now I know my x bar for this sample is 49.52. My standard deviation of the population's estimate, unbiasedly, is 2.74. N is 20. And so it magically calculates degrees of freedom of 19 and uses that particular t-distribution. And I want it, because the null I'm looking to find whether it's less than the null hypothesis, and the color doesn't matter. I'm going to calculate it here. And so now I get all these values here. And so what I can see is my test statistic is t is equal to negative 0.783. My p-value is equal to 0.2215. So if I round that to 3 significant figures, is 222. Okay, and so what this is saying is, if I assume my null hypothesis is true, right? And if my null hypothesis is true, then I'm making a sampling distribution where my mean is 50. The standard deviation would be the 2.74 over the square root of 20, because that's using the central limit theorem. And what it's saying is that to get this mean of 49.52, which would be here, 49.52, I could get that value 22. This area here is 0.22. So 22.2% of the time, I get a value as extreme or more extreme of 49.52 if 50 is true from this particular random sample. So that's not very rare. And so to reiterate what the p-value means, if I consider what the p-value means here, what I can say is, if the mean weight of the M&M bags is 50 grams, then the probability of finding a sample of 49.52 grams or less in a sample of 20 is 0.22. That's what that p-value, this p-value we calculated, that's what it means. And so we have our normal distribution. We have our p-value here. This is the 49.22. And this is our area of 0.222. Now, my alpha value is 0.05 here. In order to be significant, it would have to be in this region here. And because my p-value is so large, what I will do in my conclusion, and I have to say as the p-value is bigger than alpha, which is, this is 0.22, is bigger than 0.05. Therefore, I fail to reject the null hypothesis and conclude insufficient evidence, to say the M&M Corporation, the M&M bags of are the M&M, insufficient evidence to say the M&M bags are less than 50 grams on average. So I have to make the conclusion with a reason, a p-value compared to alpha. And there's going to be more, an extra video on explaining these in detail, because this is not a simple concept. And I have to make the conclusion, because the p-value is so large, I fail to reject H naught. And I have to conclude insufficient evidence to say the M&M bags are less than 50 grams on average. And so I must conclude, in doing this conclusion, I have to talk about the null hypothesis, and then I have to say sufficient or insufficient evidence about the alternative hypothesis in context. Okay, it has to be in context. And so if we think about what this is talking about, right? If you think about a person on trial in the United States and in many countries, you are innocent until proven guilty. Guilty, right? Well, innocence is the null hypothesis. And you are innocent until there is enough evidence to say that you're guilty, within a reasonable doubt, right? You have to have supporting evidence, have sufficient evidence to say that you are guilty. This is the alternative hypothesis. And so we assume innocence to try to prove the guilt. The same thing happens with our null hypothesis and our alternative hypothesis in the hypothesis test. We assume the status quo of what's happening now, and we try to show the new thing going on. The more evidence you have to support the alternative, you can then reject the null hypothesis. There's your introduction to hypothesis testing. There's a lot more to come.